This meeting is being publicly streamed.
All right. Uh, good morning, everyone. So this is week four. Uh, can you see?
I mean, sir, previously it was visible, but right now it is not.
Okay. Yeah.
I mean, I don't know about others, but I am not able to see anything right now.
It's visible, sir.
Screen is visible for me.
Okay, then probably it's some issue from my end.
Is it visible now? Just a second.
Sir, if you don't mind, if you just can explain two questions I have. Actually, I have to leave for a
Yeah, I will
meeting.
do. I will do. Uh, yeah, I will do once this session at the end of the session once I cover today's material. Is it visible now?
Okay. I mean, for me it is not visible, but
For
probably
me,
it's
Yeah,
it's
because of
it's
my.
No, sir, not
it's not
yet.
Yeah,
visible. It's not visible.
yeah, it's not visible actually.
Right. Yes, I think now the presentation is visible. Uh, we
Yes, sir.
can
Now it
start.
is visible. And sir, like, is there any G space whereby we can ask doubts, or should I just post on discussion forum only?
Yeah, you can post on discussion forum. That is the one place, and then there is a Google group also with all of you guys over there, so you can
But sir,
post your doubt over there.
I think
You can have a discussion.
I think I'm not added in that G space.
Uh, you must be if you are enrolled to the course. You must be added to that.
Hmm, is there any way to check? Okay, one second. Let me check.
Yeah, we will discuss that later. So let me start with the lectures anyway. Quite clear. Correct. I will share you the what can I do? I can write down the link of that group. If that's possible.
Sure, sir.
You will do. It's not showing me. Any link is not showing me. If any one of you is in the group and can share the link of that group, you can please do so in the chat. I hope everyone has the chat access. All right. So in today's discussion, we are going to discuss linear transformation in higher dimensions. So what do we mean by that? So you have already seen linear transformations for vectors in R2. Okay. So what is a vector in R2? It has two coordinates. Okay. Now in a higher dimension, it may have more than two coordinates. It can have n many coordinates, where n can be some uh, natural number like 3, 4. Okay, it could be a vector in R3, it could be a vector in R4, and so. So on those spaces as well, there are plenty of linear transformations that you can have. So uh, so so let me first start with recalling what is the linear transformation on R2 to R2. Okay. So this is you have already seen. So I'm just recalling this. So a transformation uh, from R2 to R2, where a transformation means a function. Okay. From R2 to R2 is said to be linear if it satisfies these two conditions. Okay. What are these two conditions? These two conditions are called the linearity conditions. Okay. Uh, so you can just directly generalize these conditions into high dimension as well. So first condition is that it uh, distribute the function applied on the sum of two vectors is equal to the function value of the vector, the sum of their function value. And if you multiply a scalar to a vector and then you apply a function on it, then you can take the scalar out. So these two conditions are called the linearity conditions. Okay. So and you have also seen a lot of examples of that. So let me just write down a few. So for example, I'm taking function from R2 to R2, so that is being understood. So let's say you take an example of like this, uh, x plus y plus 3x plus 2y. So this is an example of a linear function. Now you tell me whether is this an example of a linear function or not. So are these an example? So question
First
is,
one yes, second one is no, and third one is yes.
third one is yes,
Third one is
second one
yes,
is
but no, because their degree is 2.
okay. Do everyone agree with Ananya?
Yes, sir. The second one is not linear.
What about third one? My claim is third one is also not linear.
Yes, sir, because there we have extra 1 and 3, which will make it not linear. Because when
Okay,
we
can you
apply
come up with
linear,
a yeah, yeah, continue.
if we apply some random input, so we will get something like it will not follow the addition and scaling thing.
Right, that is right. One simple way to see this is as the linear maps takes origin 0.0 vector to 0 vector. Okay, so if you take 0 over here, it will take 0 to 1 comma 0. So this map takes 0 comma 0 to 1 comma 0. So this is not a linear map. This is another way. See? All right. Good. So you guys have recalled what is the linear transformation. It satisfies these two conditions. Now we have also seen that with respect to a canonical basis, what are the canonical bases? Canonical basis is a choice of vectors of your vector space uh, that satisfy two conditions: linear independency, and they span the whole R2, right? So what is a canonical basis? Canonical basis is a specific choice of vectors. So what is the differentiation of 1 comma 0 and 0 comma 1? Those are called the canonical basis of R2. In our case, the domain and codomain are R2. So domain is also R2, codomain is also R2. So we have this canonical choice. And now with respect to these vectors basis, you can represent your linear transformation by a matrix. Okay. How do we so? So in order to do that, you write down the image of vector 1 comma 0 under T, you will get, and then you express it with the basis of the codomain. Okay, because the image of a vector will lie in the codomain. So you will express that again with respect to the basis of the codomain, which is again the canonical basis. So you will get some coefficient a11, a1, a21, and similarly for 0, 1 also you will get some coefficient a12 and a2. Now these coefficients you can write it down in a matrix. So this part you have already seen how to get a matrix representation of a linear transform. Now your A uh, is going to look like this for a given linear transform. Now let's look at some. So for example, let's take this example. So we have already discussed one linear transform. So let's take that linear transform and look at what it's. So our linear transform was this. Now look at the uh, matrix representation of this. So where does the 1 comma 0 go under T? It goes to 1 comma 3, right? And where does 0 comma 1 go to? It goes to
1 2.
1 comma 2, right? So now following the, now I need to express 1 comma 3 and 1 comma 2 with respect to the canonical basis of R2 again. So now what will be the expression? 1 comma 1 comma 0 plus 3 comma 1 0 comma 1, 1 comma 1 comma 0, 2 comma 0 comma 1. Now you just follow the notation. Where does A11 go? A11 sits here, A21 sits here, A12 sits here, A22 sits here. So using this convention, you will get the matrix A. Following the notation, you will get the matrix 1 3 and 1 2. All right.
Yes, sir.
Excuse me.
Now, yeah.
Where did we get t 1 comma 0 equal to 1 is 1 comma 3 from, please?
From this linear transform. So in the above example, this was the only linear transform that we discussed. Other two were not the linear transform.
Also, you have just rewritten that. Is that it?
Yeah. So
Okay.
I'm using this linear transformation to get the matrix representation. All right. So now what you guys have noticed is this, that the image of the first vector, all right, the image of the first vector, the coefficients of that correspond to the first column, right? And the image of the second basis vector, in particular the coefficient of the image, correspond to the second column. So we can generalize this in order to say, so we can just simply say that A is first image of the first basis vector. The first column, the second column will be the image of the second basis vector. All right, expressed in terms of the canonical basis. So just keep this in mind. So in R2 to R2, so you have observed this. Okay, so this is the recalling part. Now let's get into the multi-dimensional or high dimensional linear transformation. Okay, so following the same pattern, we start with a function which is a function from Fn to Fn. Now what is Fn? Fn, where F, as following the notation from the lecture, F could be R or C. Okay, so what does Fn mean? Fn means simply means set of elements, set of n numbers. Okay, so basically a vector which has n coordinates. Sorry, let me use a different function. A1 to an. Okay, where each ai is in f for I varying from 1 to n. All right. Similarly, you can define fm also. Okay, fm will have m many coordinates. Now a function. So now a function from now a function from uh, yeah. So now a function from fn to fm uh, is called a multivariable function. Okay, so you will not get just one function; it is multifunction on multivariable because you have n many variables over here, uh, and you are getting m many functions on the right. So is a mapping. So a linear transformation is a map like this from Fn to Fm that associates every input vector u in Fm to an output vector v. Okay, to an output vector v that sits inside Fm, satisfying the following conditions. Okay, again there are two conditions, which is directly generalization from the R2 to R2 case. So the scalar multiplication, the scalar, if you multiply scalar with a vector, the scalar will come out under the transformation. And T is linear. In particular, if you apply T on the sum of two vectors, then it distributes. Okay, in this way. So these are the two linearity conditions that you will follow uh, in in higher dimension as well. So let me write these things in more detail. So let's say you will have C and you have a vector U which is of this form. All right. Then what happens is that C will come out and you will still be applying it on the rest of the vector. And similarly, if you have A1, B1, and so on up to AN, BN, then it is equal to A1 up to AN plus B1 up to B.
Excuse me, is it just me or can everybody else see the writing?
Oh no, I
No,
think
it's
it's
also stuff for me.
I mean, I
Me
think, yeah,
also.
it is interrupted.
just wait for a second. Let me figure out what happened. Oh, okay, it's that. All right. All right. Yeah. Now can everyone see this? Great.
Yes, sir.
Okay, so now let's take an example of these linear transformation. So let's take this. Let me write it. Yeah. So consider this example of linear transformation from R3 to R3. So in this case, you can notice that N and M are same. All right, where N and M need not to be same always, but in this case, I'm taking M and N to be same. Okay. How do I define my transformation? So my transformation is defined X, Y, Z, uh, T of X, Y, Z, maps to 3X, Y plus. Okay. So it is 3X plus uh, Y plus Z, 0. So you can check that it is a linear transformation. Okay. Why? Because it satisfies the two conditions. So let's do that. First condition is the if you multiply any scalar, so let C be R. So if you multiply C with this vector, which in particular means Cx plus comma Cy comma Cz, and then you apply the function over it, you will get 3Cx comma Cy plus G 0. All right. Now, now what you do? Now you take the right hand side. So what's the right hand side? Right hand side is T times X y Z. C is this. X y Z is X 3X Y plus Z 0, and after multiplying it you will get 3X C Y plus C 0. So you can see that right hand side and left hand side are equal. So you can conclude that TC of some vector XYZ is equal to CTXY. Okay. Now similarly, if you take two vectors also, x1, y1, z1 plus x2, y2, z2, and you look at and you take their sum, then it will give you some vector like this. And then you apply T over it. Then it is same as applying T over this sum vector. And the result of this is precisely this. Now you do now you apply on separately. Okay, so you apply this and this first. So you will get 3x1 y1 z1 0, 3x2 y2 z2 0, and the result here will again be this. Okay. So again, you can see that the right hand side is equal to the left hand side. All right. So,
Excuse me.
yeah,
If we look at this transformation that you have written, in the
yeah,
third coordinate you have put a 0. If we put
yeah,
anything non-zero over there, then again we will have the problem that the origin will not go to the origin, correct?
yeah. It won't be the linear transformation then.
And stop being linear. Is that how it works?
Yeah, it will not be. You can check that when you take, suppose if you take, let's say k sine, k which is non-zero. Okay. Suppose you defined your t like this, 3x. I will keep my first two coordinate as it is, but instead of uh, third coordinate, I put k. So now k I put. So now if you take, uh, if you add two vectors, okay, x1, y1, z1 plus x2, y2, z2. So what this will give? This will give us t of x1 plus x2, comma y1 plus y2, and then z1 plus z2. Right. Now you look at the image of this 3 times x1 x2, uh, and then their sum, and then uh, it will be just k. But if you perform it on individual entities, and let's say this plus this, you do that. So this is separate. Let's keep it separate. This is this expression over here. If you perform the individually, then what will you get? You will get 3 1 x1 y1 z1 plus k, and then something with third coordinate also. Okay, if you add these two things, you will get 2k, which will not be equal to this unless k is equal to 0. Right? You get the point?
Okay.
Yeah. So you can check the linear transformation conditions, and the linear transformation map need not to be always when n is equal to m. It can be when n need not to be equal to m. All right. So again, in the case of like in the case of in R2 in vector space was R2, you have basis vector. Similarly, in this case, in high dimension also, when you are working with vector space which is Fn, okay, and coordinates vector, then also you have a concept of vectors. So let us first recall what is the basis vector. Sorry, basis vector. So let us first recall what is the concept of basis vector in for vector space R2. So set of two vectors v1 v2 in R2 are said to be basis of R2 if they span the whole R2 and they are linearly independent. So what do I mean by span? By span, I mean that any vector in R2 can be written as the linear combination of.
Excuse me, sir.
Yeah.
Actually, in week one, we studied along with the basis definition, whatever you just told. We have the spanning set definition also. So can you just tell me the difference between spanning set and basis? I
Can
mean,
anyone
both
tell
the
me?
definition.
Can anyone tell the difference between spanning set and basis in case of R2?
Yeah, in case of
Unique,
R2.
sir, it is unique, linearly
Uh,
independent.
okay. Anyone
Like
else?
I guess in some ways it's the same meaning, but I think in a span we can have some uh, dependent vectors also, but in basis we can't have the dependent vectors.
Right. That is a correct distinction. So spanning set is the minimal span. Okay, it's the minimal number of vectors that can span the whole vector space. That is what it means. So bases are always a spanning set, but not every spanning set is a basis. Okay, do you understand, Aditya?
Yes, sir, I got it. I think so. Basically, you can represent spanning set as the linear combination of, I mean, two vectors which are basically spanning. Is that what you mean?
No, spanning means that spanning. If you're saying, let's say two vectors span R2. Okay, what does this
Yeah.
mean? That any vector in R2 can be written as a linear combination of these two vectors. That is what it means.
Okay. Okay. Sure.
So,
Okay.
but what is a basis? Basis is the minimal spanning set. What is the
So
minimal spanning set?
in case of basis, those two vectors must be linearly independent. But in case of spanning set, they can be linearly independent and they also cannot be linearly independent.
If they are not linear independent, then they cannot span whole R2 unless you have more than two vectors. So, for example, let me
Ah,
take an example. So, let's take this example 1, 2, 2, 3, 2, 0, 0, 3. Okay, so if you look at this set, so if you look at the span of this is R2. Okay, but this is not the
okay.
basis. This is not a basis
Correct.
because this is not the minimal spanning. What will be the minimal spanning? As you can see that the first two vectors are dependent. All right. So you remove one of the vector and then uh,
1, 0 and 0, 3
you
are the
remove,
bases.
yeah, yeah.
Hmm. But can we speak that 1, 0 and 2, 0 are the spanning set?
No, 1, 0 and 2, 0 are not the spanning set. Why? Can you tell me why it's not a spanning set? Because 0, 3 is not
I
empty.
know.
0, 0, 3, you cannot produce 0, 3 from 1, 0 and 2, 0.
Okay. But actually, they are producing one. I mean, it's a line, right? The subspace is the
Yeah,
line.
but it's not whole R2. It's not whole R2.
It's
Question is whether
okay.
it
So
span whole R2.
oh, okay, okay, okay.
Yeah, they span, obviously. Any vector span their own spanning set. Right.
Yeah, right.
Right.
Hmm.
So,
Okay.
uh, okay.
Sir,
So it
But
needs to
then in
span.
this question only, but sir, then in this question only, if you want to span whole R2, then you need bases only, right? I mean, bases are you cannot if you see there are infinite bases. So if the two vectors are not bases or linearly independent, then they cannot span whole R2, right?
Yes.
So your statement of vice versa one, ki the bases are the spanning set are included in the spanning set vectors, but all the spanning set vectors are not bases. So how is
Yes.
this true?
Yeah, I just give an example, right? Look at this example
Yeah,
again. 1 comma
sure.
0, 2 comma 0, 0 comma 0. Does it span R2? What is the span of this? It spans R2, right?
Yeah, it will span R2. Yeah.
But it is not a basis.
Okay, so this is spanning set.
Yeah.
Oh, okay, okay.
So they also it spans R2, but it is not a basis. That is what my question is, right? Not every
Yeah, I
spanning
got it.
set is a basis. Okay.
Yeah, spanning set, which is the basis, is 2003, right?
sir, sir, in short, every basis is a spanning set, but not every spanning set is a basis, right?
Yeah, that's what I just said.
Yeah.
Yes. Right. Okay.
Yes, sir.
So
Got it.
got it right. Okay, good. So yeah, so you have already seen what is a basis. So first of all, the basis needs to satisfy these two conditions, that it needs to span whole R2. The set of vectors needs to span whole R2. And the second condition is that they need to be linearly independent. Okay. So the linearly independent condition makes them that there can only be two vectors Okay, and because it needs to span also, that's why it cannot be, because it needs to span, so it has to be more than one vector, and the independent condition implies that it has to be less than 3. So that's why it has to be 2 vectors. So those 2 vectors will be this basis. Okay. Right. Now you can generalize this definition. To higher dimension case also. So in case of, instead of taking R2, I can work with n coordinate vector, which is Fn. And in Fn, you will have n vectors, set of n vectors, which you will call basis. So again, the 2 conditions will be same, that any vectors, any vector in Fn can be written as a linear combination of these n vectors, and these n vectors are linearly independent to each other. Okay. So now, what do I mean by linear independency? Uh, so can anyone recall what is the linear dependency in R2?
So the
When
vectors must be in the it should not be in the same direction. Should be in the opposite direction. No, not opposite, but not in the same direction.
Okay, but more mathematical definition in terms of
we can only make them 0 or something equals to when their a1 or a2 would be 0.
Yeah, so linear
okay, that means
combination of those vectors will be zero in the trivial case only. Is that
right,
what?
right.
Yeah.
Yeah, that is correct. That is what I was looking for. Thanks. So linear combination of these two vectors, of a zero vector. So what does this mean? That if I write the linear combination of these two vectors equal to 0, then it implies that there is only trivial solution. That means a1 and a2 all have to be 0. That is what the linear independency means. Similarly, in the case of n vectors, we will just generalize this definition, that if you express the linear combination of 0 in terms of these n vectors, then all the coordinates, all the coefficient has to be 0. Right? If you express the linear combination of 0 in terms of these vectors, then all the coefficients has to be 0. So that is what the linear independent means. And the first condition is that the spanning set of these n vectors has to be equal to f. Okay. Uh, so what does this mean? In other words, that any vector, any vector v in Fn can be expressed as a linear combination of v1 to vn. This is what it means. All right. Okay, so any set of n vectors satisfying these two conditions of Fn will be the basis. So let us look at some example. So for example, 1 0 0 0 1 0 0 0 1 forms a basis. Okay, so let's just check whether does it span the whole Rn. So you can write any ABC vector in R3 as a linear combination of 1 2 3. How? You can just write it like this. Okay, and then so it is a linear combination also, and then in order to check the linear dependency, what you will do, you will take the coefficients, you will express you will write down the linear combination of these three vectors of 0, linear combination of 0 in terms of these three vectors of 0 vector, and then what will you find out? That it will be a1 a2 a3, the sum will be a1 a2 a3 will be equal to, which is equal to 0 0 0. This would imply that a1 is 0, a2 is 0, and a3 is also 0. All right, so they are linearly independent as well. All right, so this forms a basis. We call this basis, because you guys are already familiar with this kind of basis, we call them the canonical basis. You can generalize the canonical basis in higher dimension also. You just need to, it will be 4 in number, 4, sorry, it will be n in numbers, where each, in each vector, the ith vector in that basis will have ith entry to be 1, all other entries to be 0. Okay, so these are called the canonical basis. Now let's look at this another example. So does this set of 4 vectors form a basis of R? Okay, so let's check that. So are these vector linearly independent? First of all, let's check that. -3, 3, 3 plus, so that means A1 this, A2 this, A3 this, A4 last vector equal to 0, 0, 0, 1. All right. Now 3A1 plus A2 3A1 plus A3 plus A4 3A1 A3, and then yeah, that's all. That is equal to 0, 0, 0. Now we need to equate each coordinate. We need to equate it coordinate by. So what will you get? You will get 3 equations. This is equal to 0. 3A1 plus A3 equal to 0. 3A1 plus A sorry 3A1 plus A3 plus A4 equal to 0. 3A3 3A1 plus A3 is equal to 0. Okay, so this is called a homogeneous system of linear equation. You get a homogeneous system of linear equation from this. And now let's see. From this first equation, you get that 3A1 is equal to 8. All right. Similarly, from this equation, you get A3 A3 is equal to minus 3A1. All right. From this equation, from the first equation, you get A2 is equal to 3A1. Right. Now, from this second equation, you get 3A1 plus 3A plus A3, which is minus 3A1 plus A4 is equal to 0. So we'll get A4 is equal to 0. Okay. But what you notice here that A2 is in A1, A3 is in A1, A4 is 0, but there is no answer to A1. A1 could be anything. So the solution is A1, 3A1, minus 3A1 and 0, where A1 could be any real number. Okay, so is this a linearly independent set?
No.
Sir, it's
Yes, because it has infinitely many solutions, right? So this is not an independent set. So can it be a basis then?
no, sir.
No.
It
No.
cannot. Right. Okay. So yeah. So we have seen an example of a linear independent set, and an example of a basis, and an example of which is not a basis. Okay.
Sir,
Now let's look at this.
excuse me, sir.
Yeah.
Instead solving these equations, can we directly conclude that since it is in dimension 3, right, and here it
Right.
contains 4 vector, then it is
Right.
guaranteed to be they are linearly dependent.
Yeah, but this is the proof of proving that, right? You need to prove
Okay.
that,
Okay,
right?
okay,
And how will you prove that? You will prove like this.
okay, sir.
Okay. Yeah.
Excuse me.
Yeah. Please go ahead.
One other thing we could do is we could take the third vector and then
Yeah.
let's call it v3, subtract the second vector from it, so v3 minus v2, and then multiply that by 3, and we end up getting v1, and then we show that we can express one of them in
Yeah,
terms
yeah.
of the other two.
That is also correct. That is also correct. If you can, but what happens is that it is not easy to find out the combination among the vectors. Okay, so it's better to use the uh, first principles. But whatever you said is also correct. You can do that. If you can find out the linear combination directly after looking at the set of vectors, then please go ahead. Do that. Okay.
And
All
the
right.
key idea behind
Yeah.
your way of showing this is that we cannot uniquely, give some proper numbers to each of the solutions here. One or the other variable will be dependent on some other variable. In this case, a1 is a1, and both a2 and a3 have to be expressed in terms of a1 only. They don't have any
Yeah,
unique.
because this system has infinite solution. That's
Right.
all. In case of because in case of independency, it needs to have a unique solution, which was A1, A2, A3, A4 all have to be zero, but which is not the case in this example. Right. All right. Uh, so yeah. So what is the benefit of working with basis? The benefit of working with basis is that you can express any vector in Fn uniquely as a linear combination of these bases. All right. So that is what this theorem says, that you can express any vector uniquely as a linear combination of basis vector. That means there exists unique scalars a1 to an such that you can express u in terms of these. Now, this list of scalars is called the coordinates of v with respect to the basis. Okay, and we often write v as a1 to an with respect to that basis. So you need to mention. So whenever you are expressing a vector in terms of coordinates, there in the background there is some basis that you are choosing. Okay, so usually what basis we work with is the canonical basis. Okay, but it need not to be always the case that we will work with canonical basis. If you are working with different set of bases, then there will be some mention of that. Okay, so but whenever you express a vector in terms of coordinate, there is some basis working in the background, and you can uniquely express any vector in Fn as a linear combination of these bases. So what happens now is that so instead of working with complete Fn, okay, where you have infinite many vectors, now you can just simply work with a finite set of vectors. Okay, u1 up to un, which we call them to be the basis. You can just work with the basis of Fn. Why? Because you can express any vector in terms of these bases. So it is sufficient to just work with these bases, okay, and define theory around these bases. So you have reduced the problem of infinitely many vectors, knowing infinitely many vectors, to just knowing some finite set of vectors. Okay, so that is the one of the large benefit of working with bases. All right. Moreover, uh, what you can also do is that you have a linear transformation. Suppose you have a linear transformation T from Fn to Fm, let's say, and then you have a basis u1 up to un of Fn and u1 and v1 up to vn of Fn. All right, you have two set of vectors in the domain and in codomain, right?
Sir, those
Now,
V1 and V1 to VM would be dependent on U1 to UN, right? Because it's output.
no, no. It won't be, because these are two different spaces, right? Look at think of them as different vector space. So in this vector space, there is this vectors. These vectors are the basis of this vector space. It will not be dependent. All right. So
Okay, so
now,
by the way, in the lectures, professor said that FN is input and FM is output. So
right.
that way, V1 and VM should be dependent on VN. like U1.
No, it need not to be dependent always. What do I mean by that? Yeah, for example, if you take, let's say, you work with a zero vector, zero map. What is a zero map? So zero map takes vector from, let's say, R3. So what it does, it takes xy and it maps to 0, 0, 0, 0, 0. All right. But let's say you have a canonical basis on R3. All right. So now neither of these bases in R3 depends on the image. All right. So
Okay,
it's not
sir.
always the case. Yeah. But that is correct. It is. This can be think of it as input space where you input things, input vectors, and this is the output. This is this is where you get the output. Okay. So you think of it like a bucket. So let's say this is one bucket. Okay, where you have inputs over here, input material, and then you have machine like this. You have a machine, and then you have output bucket. All right. So you take something from here, you put it in the machine, and then the output will give you something that will fall in this bucket. That's all. But
Okay,
this
sir.
bucket is already full of its own kind, so it works like that.
Okay, sir. Got it. It's like we have one function, and this U1 to UN are just input in that, and then we'll get something else.
Yeah, you will get some output, but those output can be expressed with some basis of the code only. All right. So what I'm trying to say over here is that now, because now any vector in the input space. Okay, let's take any vector here. So this can be expressed as a1, u1, a1, u1, a2, u2, and so on up to an, un, with respect to the basis of the input space of domain. And now you apply t over it. Okay, you apply t over it. So what will you get? You will get okay. So you apply t over u. So what does this t over u mean? Is that you can express t over u now in terms of, because now t over u lies in fm. Sorry, just a second. Now this t over u lies in fn. That means you can express t over u in terms of the basis of fn. So let's say this is the basis b1, v1 up to bm, vm. All right. So in particular, you can express each of the vector, basis vector of fn in terms of these bases. So there will be some coefficients to express them. Let's say. So let me write it down as a1 1 bm, a2 1 v2 up to a and 1 bm. All right. Similarly, you can express tu2, and you can also express tun. So let me write down the last line as well. You will get a1n, v1, a2n, v2 up to a vn, v sorry, amn, vn. Right. Okay, you can express each of this vector in this way. You can express each of the basis vector in terms of this way. Now, so instead of having the linear transformation finding out for each vector, you can just work with the basis images of the basis vector. You can express the images of the basis vector in terms of these coefficients, and you can, in particular, as you have done in the case of R2 to R2, you can express this in terms of a matrix. Okay, so now you can express this linear transformation in terms of matrix like this, where each, so remember, in the case of linear transformation, of from R2 to R2, we expressed in the matrix, each column correspond to the image of the first vector of the domain, first basis vector of the domain, the coefficient of the first vector. So similarly here also, the first column will correspond by the coefficient of the image of the first basis vector. All right. Now second column will be the image of the second basis vector, which is going to be this. And similarly, the last nth column will be this. So we will get M cross N matrix. Okay. In particular, what I have done over here is that if, let me write it down. Suppose T is the transformation from Fn to Fm, and U1 up to Un is a basis of Fn, and U1 V1 up to Vn is a basis of Fm, then we can represent the matrix, we can represent the transformation, we can represent T by a matrix A as follows. So A is, so the coefficient of the first vector of the domain will become the column of the column of A. It will be an M cross N matrix. So in particular, it is expressed in our as well. So like this. Okay, let's look at an example. Okay, to make this more clear. So think of an linear transformation. Think of an linear transformation T from R3 to R3 defined as follows. So we have already discussed this example. This was one of the first example of the linear transformation that we discussed. We have already proved that this is a linear transformation. Okay, so let's take the same linear transformation and consider the basis, canonical basis for R3 in domain and codomain as well. Okay. Now, then we can represent T by a matrix as follows. All right. Now, how do I express that? First, we need to write down the images of the basis vector of the domain in terms of the yeah. So, what is the image of 100? 100 image of 100 is 3, 0, 0. All right. So what if now I need to express this? Now this lies in the domain, which is Fn. In our case, Fn is R3. Okay. Yeah. So this lies in R3, which is the output space or the code. Now we express this image vector in terms of the basis. So it will be 3, it is 0 and 0 here. All right. Now similarly, I express 0, 1, 0. So what is the image of 0, 1, 0? Image of 0, 1, 0 is 0, 1, 0. So it will be 0 times this first coefficient, 1 times, and 0 times the third. And the image of the 0, 0, 1 is 0, 1, 0 again, 0, 1. Okay. So now what will be the matrix? So what will be the first column?
300.
3, 0, 0. What about the second column?
010.
010 and also third is 010.
Right. So this is the answer. So this is the matrix representation of linear transformation T. All right. So in generality, as we have already seen, if you consider a linear transformation T to Fn from Fn and basis denotes the basis of Fn, and this B1 to Bn denotes the basis of Fm, then you can express each vector in terms of the basis of your codomain, which will give us a column of A, and which will give us the column of A, and similarly here also you will get the nth column of A, and in general you will get uh, the matrix. Okay. All right. Now,
Excuse me,
yeah.
it's sort of unrelated, but could you please tell me which software you're using to do the writing?
Oh, this is my Samsung Galaxy S6 Lite.
So some software native to that hardware.
Yeah. Samsung
Okay.
Notes.
Thank you.
Yeah. So a linear transformation can be realized as a matrix vector multiplication also. So once you have associated a matrix to a linear transformation, now you can express your linear transformation as a matrix vector multiplication. Okay. So for example, so let's start with this. Suppose you have the linear transformation Fm to Fm, and you know that the image will lie in Fn. Okay, so this is your input vector. You have applied T over it, and then you will get a vector inside Fn. Okay. Similarly, now you have associated a matrix to it. Okay, so A represents the matrix associated to T. So this is your matrix with respect to the canonical basis. So you need to also always mention what basis are you taking. So when you represent a matrix of linear transformation, you need to specify what basis you are working. So with respect to canonical basis, you have expressed your A in terms of you have expressed your A like this. Now you can define matrix vector multiplication like this. You can apply you can multiply a vector to A from the left, from the right, and then this result will also lie in Fn. Now let's check whether okay, so you can express your T. So you can express your T, T of vector, let's say A1 up to An as this. Okay. So this is what you can do. Okay, so for an example, again, I take the same example that we are working with. So let's take that same example, and now let's look at the images of under these two different uh, expression of the same linear transformation. Okay. Image of 1, 2, 3 is 3, 5, 0. And what about the image under this after matrix multiplication? So you multiply 1, 2, 3 to this vector. So you multiply 1, 2, 3 to this vector. What will you get? You will get 3, and then you will get 2 plus 3. So we will get 3, 5, 0. All right. Similarly here also you can check.
990.
Yeah.
Not here, sir. Both.
At both places you will get the same.
Yes, yes.
Okay. So this, so you can express. So what you have done till now. So you have started with the linear. You have started with linear transformation. You defined it on some arbitrary space of Fn and Fn, and then because these are some huge spaces, you have reduced the problem of working with any vector in Fn to just work with some specific set of vectors, which we call bases. Now, using these bases, we have further. So among the bases also, we choose a very special type of basis, which is canonical basis, which reduces which simplifies the problem to a great extent. And then using those canonical bases, we expressed our linear transformation in terms of a matrix representation. Okay. So now whatever linear transformation you give me, I can write down it as a matrix vector multiplication. That is what I have done then. Okay. So matrix linear transformation can be very difficult to work with, but you have reduced that problem into just simple matrix multiplication, matrix vector multiplication function. Okay. So till this point, that is what we have done. And in order to do that, we have used basis of domain and codomain. So you have, in particular, we have worked with canonical basis of domain and codomain. Okay.
Sir, can you once go through it or tell what's the importance of this? Like where it is used?
What? Which part?
This matrix vector.
Yeah, this matrix vector will be used. So I will come to that because now working with a linear transformation is difficult thing. Okay, but when you have a matrix multiplication, it is simple to work. Matrix multiplication is simple to trace. So you need to understand. Uh, so these two things are equivalent in particular. So any linear transformation is nothing but a matrix vector multiplication. So that is what is happening over here. Okay. And what is the use of this? So it will be used in order to identify some characteristic properties of a linear transformation. Like what are the characteristic properties? Like what is the nullity of a linear transformation? What is the range of the linear? What is the dimension of the linear transformation? What is the dimension means? What will be the range of so what is the dimension of the range of the linear transformation? Okay. So we can tell all these things by just looking at by working with matrix and performing some row operations. So that is what we are going to use now.
Okay.
Yeah. So range and null space of a linear transformation. So what is the range of a transformation? So range of a transformation is precisely the images the images of the vectors in Fn. So this is the range of the transformation. Okay. So now, can anyone tell me is the range? So range is anyway the subset. Range is a subset of Fn. That is clear because it takes values in Fn. So it is a subspace. It is a subset in Fn. Now, is this also a subspace? Is this a vector subspace of Fn?
FM, so
Yeah, is this a vector subspace of Fn? Range of T, is it a vector subspace of Fn?
I don't think so, because it will be in like less space because it's input.
Yeah, less is fine, but is it a subspace? I'm not saying it is the whole vector space. I'm saying is it a subspace of that? You have seen subspaces, right? What is the subspace of a thing? So you just need to check whether it is closed under the operations of Fm or not. So let's take two elements from the range. So what are the two elements? Let's take these are the two elements in range. Okay. And by linearity property, what is their sum? Their sum is also, this is their sum. Now by linearity property of linear transformation, this is equal to this, u1 plus u2. So they are also in range. So their sum is closed under the addition. Similarly, by the scalar multiplication, if you take C in R in F and TU in your range, then CTU is nothing but T of C. So this is also in range. So range of T is again a subspace of Fn. So range of T is a subspace. All right. Now, moreover, we have associated a matrix to a linear transformation. We have represented a linear transformation by a matrix. So now look at this matrix corresponding to with respect to the uh, canonical basis to the canonical basis representing T. All right. Now let's say B is a vector from the input space that is Fn, and the image under then the image vector has this coordinates. Okay. So you multiply B1 to this. Okay. So you multiply your B1 to this. So you multiply your V1 to this like this. Okay. How does this multiplication go? So this multiplication will be can be expressed like this. So you are multiplying it to each column. Okay. So this will be the image vector. In particular, the range of T uh, is nothing but the column space of A. All right. Because each A1 to M1 is the column. So range is nothing but the column space of A. So in other words, if you want to know, as you mentioned, that the range need not to be the whole Fn, right? Range need not to be the whole Fn. That is correct. But what subspace will it be? What will be the dimension? How small will it be? Or when can we say it is the full? When can we say it is the full vector space, and when can we say it is not the full vector space? And if it is not the full vector space, what will be the what is the dimension of that? How lesser it is? Okay, these are all the questions that we want to answer. So for that, you need to know, you need to find out the basis of the range, or you need to find out the dimension of the range. Okay, now what is the dimension of a subspace? Dimension of a subspace is the number of vectors in basis. All right. So we need to, in some sense, we need to find out the basis of the range. And how do we do that? So as from this observation, that range T is nothing but the column space of A, we can just find out the basis for the column space. All right. So the dimension of range will be just nothing but the dimension of the column space. And what do we call the dimension of the range? There is a specific name to that. We call the dimension of the range to be the rank of the matrix. Okay, so this is the definition. We define the rank of a linear transformation equal to the dimension of the range, which is equal to the dimension of the column space. Okay, so let's look at this example. So, and let's find out the dimension of the space. Find out rank of A. Okay, so what do I mean by rank of A? So obviously we have seen that this matrix represents linear transformation of T. Okay, which linear transformation? This linear transformation. X, Y, Z going to 3x, y plus z, 0. All right. Now let's find out the rank of this. So how do I find out the rank? We need to perform row operations. Okay. Can anyone tell me what row operation I can perform on this, or is it already in the?
It's
It's
already
already in row echelon form, right?
It is already in row echelon form.
Yes, sir.
But are all leading entries equal to what?
No.
we
First,
can change.
row one we divide with 3.
Right, 1/3. So that's the only operation that we need to do, and then we are in the row echelon. Right. Now, how many non-zero rows are there?
2.
So what will be the rank of this matrix?
2.
Right. So the rank of this matrix is precisely 2. Right? So what is the so the rank of A is 2. Moreover, the dimension of T is the dimension of the column space. Now, what is a column space, or how do we find out the dimension column space? So wherever the leading terms appear, those columns. So the leading term appears in the first column and the second column. So look at the first column and the second column of the original matrix. So this is the first column, this is the second column. So they correspond to the basis of the column space. So what is the basis? So basis of column space of A are precisely 300 and 010. Okay. So they also form the range. They are also the basis for the range of T. Okay, so they are also equal to the range of uh, basis of range. In particular, the rank of T is also equal to 2. So as you have noticed in this, that number of the row rank, which we call to be the number of non-zero rows in the echelon form, is also 2, and the column rank is also equal to 2. So they are always equal. Okay. Why? Because we only look at the number of leading terms. Okay. So the leading terms, wherever the leading terms appears, those columns uh, we look at, and the leading terms also correspond to the row rank. Okay. So row rank and column rank are always equal. So let me just write it down. Row rank of a matrix A is equal to the column rank of a matrix A, uh, and this is what we call the rank of a matrix, rank of A, either of that, right? What is the row rank? Number of non-zero rows in REF. What is the column rank? Number of yeah,
Number of column with leading ones.
yes, with
Number of
leading
columns. Pivot leading ones.
with pivot variable, pivot leading entries. All right, and they are both are same. because if there is a row which has a leading term, then it is not, then it is a non-zero row. So you will count it. And if there is a non-zero row, then it must have a leading term. So you will also count that column. So number of leading terms are same in both of the cases. So they are equal. But that is good. And that's
Excuse
how
me.
you find out. Yeah.
This is only true for square matrices or for every matrix?
Every matrix.
Row rank and column rank will always be equal.
Yes.
Okay.
All right. Okay. So now let's look at what is the null space of T. So null space is set of all vectors in Fn such that the image under the transformation is equal to 0. All right. Yeah. So is again the question is same. Is null space is also is a subspace of domain? Now, null space is a subset of domain. It is not a subspace of the codomain. So now question is it a subspace of domain?
So it will be false, right?
No, it is correct. It is also subspace of domain. Again, you can check. So it is a subspace. Is a subspace, and let me write it as an exercise for you guys to check.
So subspace is like a big set in which we have other things like Fn or something. So how that
No, no,
Fn
no,
isn't.
no. Subspace. What is a subspace? Can anyone recall subspace?
Closed under addition and scaling.
That is true, but it is also a subset of the bigger vector space, right? Any subset of a bigger vector space which is closed under the addition and the scaling coming from the bigger vector space is a subspace, right?
Yes, sir.
So can you check whether it is a subspace or not? You first need to check whether it is closed under linearity or not. So take two vectors in the null space of T and look at whether there some lies in the null space or not. And similarly, you take a scalar and you multiply scalar and check whether it also lies in the null space or not. These are the two conditions you need to check. Okay. Okay, so it is also a subspace of Fn. And again, we have the matrix representation of a linear transformation T with respect to the canonical basis.
Excuse me, sir.
Yeah.
So is null space means like it will only contain zero vectors, something like that, or it is only which will make vectors zero?
No, it contains zero, but it is not always contains zero. There can be set
So
which
why is it
there
said
can be
null space?
because it's a pre-image of zero. It is set of all vectors in Fn whose image is zero. That's why it's null space.
Okay, sir.
Okay.
It's like
Yeah.
if we are giving input to any function and we are getting zero as vector,
Zero.
then it will go to null space.
Yeah, that vector will be in null space. That vector in domain is in null space.
Okay, sir.
Look
Got
at
it.
this definition. Yeah, look at the definition. Okay, so suppose A
May I say
is
something? May I say
yes,
something?
yes, yeah,
Uh,
please.
One thing, if you could take into consideration, the lectures we already have a lot of, theory and symbols and all that. I think
Right.
it would help if we could have more of the, problem solving things in the live session. If you could please consider it, because
So the
after
problem
looking at
solvings are
A,
for
B,
TA
N,
sessions.
N so for
Okay,
so
let me say.
it's
So
just
TA sessions are meant for the problem solving. I'm here to revise the concept. I will discuss things with the examples. So yeah, I will. What I will do next from next time, I will have more examples, but I also need to cover a theory part.
Sir, also the visualization part, like we are not sometimes able to understand in this real life these things.
It is not always possible to visualize most of the things.
Yes, sir.
Okay, so null spaces again. Uh, yeah, so null spaces. So now, if you write down this expression in terms of the matrix representation, this is what you get. Okay, where V1 to Vn are varying in Fn. Okay, set of all. Okay, so it should be reversed. It should not be. Okay, so tell me one thing. Is it with my lecture that is more theoretical, or is it with everyone's?
So is it this thing with everyone?
Okay, okay. All right. So what do you guys want? You guys want more example to be discussed,
Yes,
or
more
what?
examples.
Because the
Uh,
problem is, yeah, the problem is that we also need to cover theory. If we discuss more examples, then and we solve examples with you, because solving examples takes a lot of time. So it will be difficult to pack all these things together in just 2 hours. So either we need to sacrifice on covering material, but that we cannot afford to, because there are TA sessions which are meant for the discussions, like solving activity problems, discussing examples. Okay, so these live sessions are meant for discussing theory. So and examples wherever it fits in. But we cannot entirely dedicate a session to just discussing examples. So we won't be able to do any theoretical part, which will be uh, yeah, which is not good, because we are meant to do that. So okay. So
Maybe we
nullity,
could find a way to discuss theory using the example. Is that possible to do?
that is what I'm trying to do, right? I am doing that only. So as you have noticed earlier that I've started with examples, I'm doing theory with examples. Don't you find it in that way?
See, it's only my personal opinion, so I cannot say for everybody. But
No,
personally,
I'm asking you only because you are telling me.
after seeing a bunch of A, B's, M, and N's, it feels like I don't want to see the
Look, these
alphabet
notations are
anymore.
important, because these notations are important. You cannot uh, go without these.
That I understand. It's okay.
Yeah.
I'll find some middle ground on my own end. It's okay. Please continue.
Right. Yeah. So the null space, if you write down this definition of null space in terms of the matrix vector multiplication, so this turns out to be like this: set of all vectors v1 up to vn in Fn, where you have a matrix vector multiplication equal to 0. All right. Now, if you solve this equation, now if you solve this matrix presentation, what will you end up with? Now, the aim is to find out the null space. What is the null space? Okay. And what is the dimension of this null space? Uh, what kind of subspace does it form inside your domain? Okay. These are important things to know. Because these are characteristic properties of your linear transformation. You want to understand your linear transformation, so you need to know all these things. So these help you to classify or characterize your linear transformation. Okay. Now, it turns out in the terms of the matrix representation, it turns out to be this. Now, if you solve this thing, it gives you a system of linear equation. Okay. So if you look at this, it gives you a system of linear equation, which is homogeneous system of linear equation. Okay. Let me take an example. So in the previous example, we had this matrix, and now let's find out the null space of this linear transformation. So in particular, you need to solve this equation. You need to find out B1, B2, B3 such that satisfying this equation. So how do you solve this system of equation? You convert it into an augmented matrix. You have already seen this. You convert this into augmented matrix, and then you convert the coefficient matrix in terms of the in terms of uh, you convert the coefficient matrix to the row echelon form. Okay, and you have already converted this. You can just perform this one operation, which is R1 by 3, and then you will get a row echelon forms. In particular, row reduced echelon form. Okay, it doesn't change anything on the constant vector because we all the entries are 0. So now you solve this. So you solve this. How will you solve this? It is like this: x y z equal to 0 0 0. Or
From here we will get x is equals to 0.
let me take the same vectors v1 v2 v3. So b1 is 0
And then
and
it will be
b2 is
b2 plus
minus
b3.
right. So the
Yes.
null
And b3 is
space,
equals to 0.
no, v3 is not equal to 0. There is
Okay,
no
so it
equation
will
that
get
is
multiplied to 0.
no. V3 is going to be a random, is going to be any scalar r. Okay.
Okay, sir.
Yeah. So this is what you get. And now the null space, you can write it like this: v1 is 0, v2 is minus b3, and b3 is b3, and b3 is varying in r. So, so this is what your null space is going to be. Okay. Now you can, what you can do, you can take, in order to find out the basis, what you can do, you can take b3 common, because b3 is common in this factor. You can take b3 common and you will get this, right? The scalar multiplication. So the vector that you will get over here is going to be the basis. So this is your basis vector. So this is your basis of null P. In particular, what is the dimension of, then what will be the dimension of null T?
1.
1, right? Number of vectors in basis. All right. So you have find out the dimension of nullity, and we call the dimension of nullity the nullity. So nullity is called the dimension of null space. All right. So yeah. So we have find out the dimension of null space as well. So now let's take this example and summarize all the theory that we have just discussed. Okay. So let's take an example. So it's a map from R4 to R4, and the map is given by this, given like this. First, we need to find out the matrix A with respect to the canonical basis of the domain and codon. So can anyone tell me what is the canonical basis of R4?
1 0 0 0 1 0 0 0 0 1 0 0 0 0 1.
Does everyone agree with that? Okay. So these are the set of, this is the canonical basis. Now let me write down the matrix of A. So how do I write? First, I need to express each basis vector under transformation. So what is the first image?
So what's that W?
W is the fourth variable.
Okay.
It's an R4, right?
Yes, yes.
So what is the
1
image of the first?
1 0 3 0 3
And
0.
is it okay? What about this one?
1 minus 1 0 0. 1 1 2 0. 0, 1, 0, 1.
Right. So now you can also find out, because it's the canonical basis. So the coefficient will be just, so let me write out in shorthand notation: e1, e2, e3, e4. So it is 3 e1 and then 3 e3, 1 e1 minus 1 e2, right? And so on. So what will be the matrix? Matrix is the column. So column becomes, so expression of each vector becomes the column. So it is going to be 3 0 3 0, 1 minus 1 0 0, 1 1 2 0, 0 1 0 1. Okay. So this is the matrix representation of with respect to the canonical basis. Now let's find out the basis for range of T. Okay. So basis for range of T is what? Is equal to the column, is equal to the basis of column space of T. Okay. So how do I find basis of column space of T? Sorry, not T, of A.
So first we will apply the row operations. Then we, if
Right.
these vectors will be independent, then we can call them basis.
Right. Right. So yeah. So apply, so A converted into RREF form. Okay. And then uh, columns with leading entries. Column is in the original matrix will correspond to the basis. Basis of the column space. So I leave it an exercise, this next exercise. Now, what about the basis for null space? Basis of nullity. Basis of nullity means that you need to solve this system of equation.
So sir, isn't this like we are checking if they are independent or not?
What?
This nullity, because in independent we also do the same thing, equate it to 0, 0, 0.
Right. Yes. You are checking whether these column space are independent.
Okay, sir.
Yeah. And it will not be independent in case uh, it will not be independent in case you get in case you get a more than one solution. Okay, there's always one solution which is 0 0 0, but if you can get any other solution than 0 0 0, then it will be dependent. So that is what will correspond to the null space of that. So you solve this, so you will find out some null space associated with it. Okay, so I will leave it to an exercise for you. Okay, so now let's discuss this linear dependence lemma. So what does this linear dependence lemma tells? Is that you can have, you have a suppose you have a n set of vectors which are linearly dependent. Then there exists j in Vj such that it lies in the span of the first j minus 1 vector. In particular, you can write down the span of the whole n vectors by just after you can remove Vj, because Vj is in the span of the first n vector, so you can remove Vj and the span remains as it is. Now, for example, I took an example earlier which was minus 3, 3, 3, 1, 0, 0, 0, 1, 1, and 0, 1, 0. All right. So now in this, yeah, yes. So now in this, we know that this is an independent set, linearly dependent set. All right, that is what we have proved earlier. So now this is your V1, this is your V2, this is your V3, and this is your V4. Okay. So what you can do now, you start with one by one. So V1, V2, V3. If you look at V1, V2, all right. If you look at V1, V2, V3, look at this combination. You can express your V3 as the linear combination of first two. How? V1 plus V2, you can just 3 times add V2 and you can divide 1 by 3 from V1 and you can write V3 in terms of. So what does this mean? That V3 lies in the span of V1 and V2. Okay. So you can remove, so the span of V1, V2, V3, V4 is nothing but the span of V1, V2, and V4. Okay, because you can write down V3 in this span of V2, V1, so you can remove that vector from your span. That is what this lemma says. You can do this in general, given any linearly dependent set. You can do this, and you can get these two things done. All right. I'm skipping the proof because uh, you guys don't want me to do that. So, and you can find the proof in the lecture also. So, spanning set contains a basis. So, in the beginning of the lecture, we discussed this point that every spanning set is not a basis, but a spanning set contains a basis of the span. Okay. Okay. So suppose you have a span of vectors v1 up to vn given by S. Okay. So now span of vectors is again a vector space. So in this span of vectors, we want to find out the basis of S. And how do we do that? So we will use this linear dependent lemma to yes to find out the basis. So we will start with our original set v1 to vn because that's the spanning set of S. And now for each j, okay, we will go one by one. We will try to find out whether Vj lies in the span of these the first j minus 1 vectors or not. If it does, then we can remove this Vj from V, and then whatever is remaining, you will get it as the basis. So let's look at the example again that we just discussed. So minus 3, 3, 3, 1, 0, 0, 0, 1, 1, 0, 1, 0. So if you look at the span of this and you call it to be the S, and you want to find out the basis of S, so what you will do? So we have noticed that if you start with V1, So V1, there is no vector before this. So V1 has to be in the basis. Okay. So V1 has to be there. Now if you look at V1, V2. So clearly V1, V2 are V2 cannot be written in the span of V1. So V2, so 1, 0, 0 does not lie in the span of -3, 3, 3, right? So V1, V2 will stay. Now look at V3. So V1, V2, V3. But we notice that V3 was 1 over V1 plus 3 times V2, which implies that V3 is in the span of V1 and V2. So we need to remove by this procedure, we need to remove V3 from the basis. So we remove this. So now again we are left with V1, V2. Okay. So we started with this, we get here, and then again we removed V3. Now we add V4. So now we add V4. Again, V4 is not in the span of V1 and V2. Okay. So we keep V4. So V4, so now this is what the basis is. So now B is a basis of S. All right. Does this make sense?
Yes, sir.
Okay, good. Now uh, we just look at the spanning set. Now, given a subspace of a vector space, so you can extend a basis of a subspace to a basis of a vector space. All right, by using again the linear dependence lemma that we just saw. So, suppose you have a basis for a subspace given to be u1 up to uk. Okay, where k can be equal to or less than n, uh, and you start with any basis v1 up to vn of fn. All right. Now we use above removal procedure, dependence removal procedure, uh, on the following spanning set of fn. So what you can do, you can consider the spanning set, which is by taking all the vectors together. All right, you can take all the vectors together, and you will look at the span of this. Right. Now you perform this operation dependence removal by taking first look at v1 u1 first vector u1 and then up to k and then k plus 1 up to k plus 1, and then you remove the vectors which are dependent or which lie in the span of the first uh, vectors. So at this point you will be, yeah, at this point after performing this operation you will end up with a basis. Okay. Now you the first k vectors will remain as it is because you started with the basis for a subspace. So they are already independent. They do not lie in each other's spanning set. So they are already independent. So you will get first k vector as it is, but as soon as you start moving from u k plus 1, either they will be independent or they will be dependent. As if they are independent on the first k vectors, then you remove that. If they are not, then you keep it, and then you look at the k plus 2 vector. Again, repeat the same thing. If they are dependent on the first k plus 1 vector, then remove it. If they are independent, then keep it, and do it until you hit uh, all the independent vectors. So this is how you can extend a basis to a basis of a vector space. All right.
So, can you explain that earlier thing by an example because I was not able to
Right.
understand that?
Right. Okay. So let us modify our example, previous example of it. So we were working with minus 3, 3, 3 vector in R3. So let's make it a vector in R4. 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0. Okay. So this is your, now look at the, this is your, this was your spanning set. We were looking at the spanning of this. So this, clearly this is a subspace of R3. So clearly, sorry, R4. Clearly S is a subspace of R4.
So, in the last one, there are only three vectors.
No, there were four vectors, right? There will always be four vectors. But now what I've done, instead of taking R3, I'm taking it in R4. So I've added fourth coordinate to be 0. Now we have noticed, now I need to start with the basis. I need to start with the basis of subspace. Okay. So what is the basis of, what is the basis? We have already found out the basis of this is nothing but the first V1, V2 and V4. This is what we notice. So this is the basis of uh, basis of S. All right. This is the basis of S. All right. So now what we do? Now we need to take a basis of R4 also. Look at this. We need to take a basis of R4. So let's take a basis of R4. So what basis I will take? Let's take the canonical basis. Okay. Is a basis of R4. All right. Yeah. Now we look at the spanning set formed by these two, union of these two vectors. So okay. Now you repeat the dependence procedure, linear dependence removal procedure, like the way we did in this case. Okay, you start with the first vector, look at whether it is in the span or not. But we already know that the first three vectors are already the first three vectors.
Are already basis.
Yeah. So just yeah. Sorry. Yeah. Correct. Yeah, so we already know that the first three ones are already the basis of the subspace. So we only need to look at, only need to compare the one that we have added, the newly added ones. Okay. So okay, so now look at 100. So 100 is already there. So 100 is already there, right? So we don't need to. So we can remove this. Similarly, 001 we can also remove this because this is already there. They are dependent on this. So now What about the third one? Can I remove this? Let's look at that. So now the question is, so can I write 0, 0, 1, 0 as the combination of V1, V2, V3? The answer is yes, you can. How? Let us see.
Yes,
V1
sir.
divided by 1 by 3, and then 3V2 plus 3 minus 3V3. Right?
Yes, sir.
So this also lies in the spanning of the first three vectors. So we need to remove. We cannot add this. So we have dropped this, we have dropped this, we have dropped this. Now what about the last one? Last one you cannot write. So 0, 0, 0, 1 does not lie in the span of V1, V2, V3. All right. So we need to keep this. So what is the basis? The basis is so basis of R4 is which has first three vectors as these coming from the basis of the subspace is this. All right. So this is how you this is the example of using this dependence law. All right. So this is the last topic of today's discussion, rank nullity theorem. What does it say is that? So you have noticed that we have defined uh, right. So we have defined yeah. So what we have defined? We have defined rank of a matrix and null space of a matrix here. So we have defined nullity of of a linear transformation as the number of bases in the null space, and rank of the linear transformation as the dimension of the subspace, dimension of the range, right? Which is nothing but the dimension of the column space equal to the dimension of the column space. Okay, so the theorem says that the sum of the rank of a linear transformation and the nullity is equal to number of variables is equal to the dimension of the dimension of the domain. All right. So I have a map from Fn to Fm. All right. So rank of T and nullity of T is equal to the dimension of
Sorry, is the audio muted or just my problem? Could somebody confirm?
It's muted.
Oh, okay, sorry. Uh, yeah. So we have already seen. So we have worked with this example, right, throughout the session. So A is the corresponding matrix representing T. So rank of T we have already calculated to be 2, right? Because after from the row reduce operation, you will see that the echelon form is going to be like this, and it has 2 leading terms. So the rank of T is 2. All right. Now, for null space, we did this. We reduced this augmented matrix to this coefficient matrix to the REF form, and then we found out if we solve this system, and then we found out that the basis of nullity was this. It has only one basis in null space of T, so nullity is 1. So now you notice that rank of T plus rank of nullity, rank of T plus nullity of T is equal to 3, right? 2 plus 1 is equal to 3. And what is the dimension of the domain? It is again 3. Okay. So this is what the rank nullity theorem says, that the rank of T plus nullity of T is equal to the dimension of the domain. All right.
Okay,
And how do we prove this? How do we prove this? The proof is as follows. I'm not going to discuss the detail of the proof, but let me just quickly tell. So this is the domain Fn, and in Fn you have the null space. Okay, this is nullity. The null space sits inside Fn, and the range sits inside Fn. Okay, so nullity, whatever element is in the nullity in the null space, that all goes to the zero vector. Okay, like this, they are all going to the zero vector, but it is which is part of the range, and the remaining vectors which is not in null space but they are in Fn, they goes to the vectors in range T. So what you can do, so nullity is a subspace of your domain Fn. So you start with the basis of nullity, okay, and then you extend it to a basis of Fn by using the dependence removal formula that we just saw. Okay. So how will you do that? So, and you extend the basis to Fn, and how and what is the way to do that? So you look at the basis of range of T also. Okay. So range of T basis. Now basis of range of T can be described by some of these elements: T of B1, T of W1, T of Wn minus K, where these Wi's are elements in Fn. Okay, and their images are in the range. So you look at these Wi's, and then these Wi's together with the null space, basis of the null space, they form the basis of your domain. Okay, so and what were the basis? What so this? How many number of basis vector were there? It was precisely the rank of T. And how many basis vectors were here? It is precisely the rank of nullity of T. So the nullity plus rank of T is equal to the gives you the number of basis of Fn, which is the dimension of Fn. So that is what the fundamental theorem of uh, linear transformation is. So you can do the same. So it's an exercise. So I discussed an example in between which I didn't finish because I left it for you for your exercise. So find out, verify the theorem also. So let's add one more part to it. Verify rank nullity theorem as well. All right. Okay, so we stop at this point. Yeah, I will keep your advice, your suggestion in my next session. I will try to prepare my lecture in such a way that there will be examples discussing in the first hand, and then there will be the theoretical part. So I think it would be better for you guys to follow.
Yeah,
Okay.
thank you.
Yeah. So let's stop today's lecture. and then we will meet on Friday.
One question, please.
Yeah.
We are submitting our subjective assignments in the Google Classroom. And as far as I know, there is supposed to be some peer review that will happen. How is that going to work? Could you please explain the system for that?
As far as I know, there is no peer review. We will review your assignments. We will grade your assignment. You will get to know the marks.
Sir, in the chat box, Lavanya ma'am has said there is no peer review for the Maths 2.
Yeah, that's what I'm saying. There is no peer review.
Nothing of the sort where we get to
No.
see other
No.
people's assignment and we send feedback.
No.
Nothing of that sort.
No.
Okay.
We will be grading your assignment.
Okay, thank you.
Yeah. Okay, everyone. See you on Friday then. Bye.
Thank you, sir.